Accretion flows. Okay, so good. So I'm going to talk about this difficult but also frustrating problem of high frequency QPOs in black hole, accreting black hole systems. And this problem has been around for some time. This is a famous diagram, famous plot from Raminad and McClintock. And there's a very nice update from a paper by Tommaso Belloli last year. Okay, so the phonology is frustrating. This problem is a frustrating, difficult theoretical problem because the phonology it's more or less well known, and here are the basic facts about high frequency QPOs, right? And we're going to hear more about it probably later this week by Ron or maybe Marcel talk about this thing. But this is the basic facts for simple-minded theorists like me. So here's what I remember, okay? And this frequency, high frequency QPO frequency range from 40 to 450 hertz. With these values are comparable to the orbital frequencies at ISCO. Okay? That's why they're relativistic phenomena. And the frequencies are more or less stable. The frequency change by less than 10% when the mass equation rate change by a factor of a few. Okay? And in some systems, there may be 2 to 3 ratios in the frequencies. And these are very transient phenomena and very weak QPOs. Typical amplitude variation is 1% or less, very low Q, and they only occur in the so-called intermediate state or transitional state or very high states at different terminology. And this is the same states, I come back to this is the same state at which episodic or ballistic jets are produced. Okay? So as I think I was reminded, I think recently by Tommaso Belloni that these high frequency QPOs are very weak signal, very transient, although they are real thing, but they are very transient. So we very much hope that this loft will be realized someday, and I think the phonology will be greatly improved by loft. Okay, so there's a consensus that these high frequency QPOs are relativistic phenomena. They therefore, in principle, can probe strong gravity. The question, of course, the big question is how you do this. So we heard a couple of talks yesterday about alternative theory of gravity. In principle, you can probe, test Einstein using this kind of things or other things. I very much hope this will be realized, but I think before that can be done, we really have to understand exactly how this connection with strong gravity works, like how you produce those QPOs. Now, it's often said there are many ideas and models about high frequency QPOs. That's certainly true to some extent. But I actually have some slightly different point of view. Let me explain what I mean. So let me briefly go through some of the well-known ideas in high frequency QPOs. Okay. Explain why there are so many ideas, but also it's also unsatisfactory, at least for a theoretical point of view. Okay. So the appealing idea suggested many years ago is that these high frequency QPOs are basically responding to orbital frequency of bright spots orbiting around the black hole, right? So therefore you have orbital frequency, maybe epicyclic frequency. You can do these kind of things. It's certainly a very interesting idea, but it needs to be worked out. Okay. For example, there are a lot of questions one can ask. Why you have this hot spot surviving in the disk for some time? Why it's not sheared away by differential rotation in the disk? What determines the radius, the location of the spot, right? Because that's directly connected to the frequency you're observing. So why you choose that particular radius? So that needs to be worked out, basically. Okay. Another very interesting idea, at least in my mind, extremely nice idea, having to do with nonlinear resonances. So this is, of course, motivated by this observation that in some systems you have this 2 to 3 ratio observed. Okay, so the idea is that maybe in some special locations in the disk, right, you have some characteristic frequencies of the test mass. They are commensurate to each other. Therefore, you can get some enhanced perturbation in the disk. Right? So that's a general concept. It's very appealing. I find it very appealing. Okay? But the theory needs to be worked out. People need to do the hard work, try to really start from fluid dynamics, the disk dynamics, to perturbation theory, and look at nonlinear effect and see whether this nonlinear effect nonlinear resonance really can work. as far as I know, the only work that's been done on this work is actually by our chair, Yuri Urak. So just to show this, this non-trivial work, you really have to do the hard work to really look at this problem. He has to look at 3-mode coupling, 4-mode coupling, 5-mode coupling. These are non-trivial calculations to see whether this resonance idea can work. Of course, Yuri did this in a very idealized setup, slender tori, so it's not really a disk, it's just a very thin, tori. Look at this fluid in a thin tori, he was able to do this calculation. But very impressive. So the general conclusion from this sort of limited study is that this resonance is very weak, right? It's very weak, so it's not clear whether this resonance idea can work. Of course, again, I think Yuri will emphasize this is idealized calculation. It's not a disk, it's just a thin tori, right? So my point of showing this is that I think this idea is very nice, very interesting, but theorists or theoreticians, people who are sitting in the room and theoreticians, need to do the work. You can't just hand wave. Maybe first few papers you can talk about these things, but after that you have to do the hard work, really calculate things, and to see whether this idea, this kind of idea, bear fruit. Okay. Another idea, also very appealing, is that these high-frequency QPOs are related to oscillation modes in a torus, an accretion torus, right? So it's not a thin disk. You have a torus with inner edge and outer edge. So you can have some wave bouncing back and forth between two edges, and you get global modes in this tori. So that's also a very appealing idea. In particular, this may be related to this black hole accretion in the transitional state, intermediate state. You may have a hot flow in that with certain size, right? So this is also a nice idea, but again, the frequency, obviously, the frequency obtained will be determined by the size, the location of the inner edge and outer edge, right? So the frequency you calculate will just determined by the size, the width of the torus, right? So then you can ask the question, what determines the size of the torus? You have to calculate the thing. Why is that the size of the torus is more or less unchanged when you change the accretion rate by a factor of 3 also, right? So this, again, it's an appealing idea, but one need to keep looking at this, keep working on this some form idea, realize this, whether this can be really realized in real system. Okay. And another idea, also appealing, is that this high-frequency QPOs may be related to the boundary layer oscillation. So here we don't have a neutron star, we have a black hole. So this may sound like crazy, but when you think of magnetic field, especially when you have an accretion disk after the black hole, the accretion disk carry magnetic fields. So you accumulate a lot of magnetic flux in the innermost region of the black hole. You could form a magnetosphere, right? You have innermost region dominated by magnetic fields, right? And outside you have more gaseous disk, and inside you have this more or less vacuum-like region of magnetosphere. So you can have boundary region between these boundary layer between these two regions, and that region may have oscillations. There's some instabilities that can happen and naturally oscillate. Okay. Again, so this is some idea we worked on also. Again, it's interesting, but it's not satisfactory because one has to understand what determines the size, the radius, the location of the boundary layer, right? Under what condition you can accumulate this magnetic flux in the innermost region, right? Because the frequency you see will be basically determined by the location of that boundary layer. Okay? And okay, so these are the reason I'm mentioning this is not because I'm not criticizing any of this. I'm just saying all these are intriguing and interesting ideas, but our theorists need to relate to the work. You can't just hand wave, maybe again, the first few papers when discovery come out, you can talk about this thing, but then after that, we really have to sit down to really do the hard work on the simulation, all this kind of things. Okay. Okay, so finally, a large class of models that have been studied over the years is a model by so-called oscillation modes in relativistic disk. And this has been worked on by Shoji Kato and Bob Wagner and others, and including our group at Cornell, and been working on this problem for the last few years. So I'll come back to this later. Before I do this, let me also emphasize, of course, as you all know, in recent years, there has been dramatic, significant progress in the numerical simulations in full generativity of black hole accretion flows. And some of these simulations are beginning to at least on the computer, see the numerical data, see the variabilities. So here's just an example from McKinney et al. They have the power density spectrum. You see some peaks, okay? So of course, one should be cautious about this. Many of these simulations are not designed. They have certain setup, designed for certain problems. For example, for galactic center, Sagittarius A stars, right? And the frequency, is not exactly very different. It could be very different from what you actually expect from the high frequency QPOs. So right. So I think this is a very this certainly is going to happen. Continue to improve the simulation, but one should always be cautious about this also, right? So I think the future theoretical progress, understanding this hard problem of QPOs really require both approaches. On the one hand, people will be continuing to improve the simulations for GR MHD simulations. On the other hand, right, one has to also continue to carry out semi-analytical work and carry out controlled studies, namely, you define your setup idealized problem, well-defined initial conditions, well-defined boundary conditions, right? And then try to calculate the problem to the end, and then see whether you get the result that the observers are giving us, and from that you can either reject the model or sort of continue to move on along the same line. So that's I think both approaches are valuable in order to gain physical insight, in order to understand making progress in this QPO problem. Okay, so now let me go back to this general ideas, models of high frequency QPOs. So focusing on this last items of oscillation mode, global oscillation modes in relativistic disks. Okay, again, this has been worked out for many years by Cato and Wagner et al. And what they have been doing is to calculate the oscillation modes, frequency, just like in the star you can calculate what kind of oscillation of the star you can have. But of course, for me, the important problem is what determines the excitation of the modes. A star can have, every star has oscillation modes, right? Have oscillation modes, but you only see oscillation, you only selected only a few stars, right? Only a certain region in the HR diagram. You see the stellar oscillation, right? Not all stars you can oscillate, right? Because nothing is exciting them. So for me, the key problem is the excitation mechanisms of oscillation modes, right? The disk accretion flow is sitting there waiting to be excited, but you have to excite it to be able to see it. Okay, these have been worked on. I'm very happy to see in the last few years. Starting from Cato 2008, there has been some theoretical approaches trying to look at these possibilities of excitations of those modes. In particular, this group, Cato, Ogilvy, and Cato has a lot of papers in the last 2 years. I think it's very impressive papers, and they have been clearly looking at the possibility of some oscillation mode can be excited by global distortion of the disk. Our effort at Cornell for the last 4 and 5 years, since we started doing this problem, it's to look at the growth of global oscillation modes due to co-rotation resonance. I explain what I mean, and nonlinear effect, the effect of magnetic fields, turbulence. So our approach is basically starting from simple things, gradually add more and more ingredient, and to see how the physics is changing. Right. So that's our approach. So in the remainder of the time, I will talk about some of our work. We summarize what we have been doing. So this is work with there are 2 former graduate students. Dave Zhang was a student a couple of years ago. He moved on to Caltech, a postdoc, and now it's McGill. Wen Fu graduated about a year ago. Now it's postdoc at Rice University. We're very happy Yuri has been working with us for the last 2 years, doing very hard calculation of fully relativistic oscillation. Okay, oscillation resonance effect, and it also collaborated with the National Observatory in China, and also the new student Ryan Miranda doing some simulations with us, controlled simulations. Okay, so the main point of our work will be just one slide summary of what we've been doing. Okay, this sign would Okay, anyway, the main point of work. So we have been focusing on this so-called P mode, so inertial acoustic oscillation or spiral density modes in the disk. These modes are different from what have been sort of focused on by Wagner et al. And Cato et al. And these modes are actually simple. I could go into the detail explaining why I believe these modes, even though it's simpler, it's actually more promising, more robust, especially when you consider a turbulent disk, whereas some of the modes they focused on, more subtle, require vertical structure, is actually can be easily destroyed by turbulence. So I think this mode actually simpler mode in the disk, okay, more easy to understand. So there are these modes, P modes, in the disk. They can be trapped in the innermost region of the disk. I explain what I mean in a minute. And these frequencies can be calculated. Okay? Under certain assumption, you can calculate global oscillation modes of the disk. They can be calculated and agree largely with observations. Okay? Not completely, there are caveats I can talk about, I'll be happy to talk about, largely with observations. And most importantly, these modes can grow due to co-rotation resonance. We call that co-rotational instability. Generativity plays an important role in this growth, mode growth. Okay? So in essence, what's happening, why the mode is growing, is because when you have a disk, you have a lot of differential rotation in the disk. Under some conditions, the energy stored in the differential rotation can be channeled into the mode, making the mode grow. So you are using the differential rotation of the disk to make the mode grow. Okay? And then we study how the large-scale magnetic field may enhance the mode growth rate. This is relevant to the problem that I mentioned earlier, that when you see these high-frequency QPOs, you also see ballistic jets. So this is, we believe this, these QPOs are also related to the production of episodic jets in these kind of systems. And finally, I'll talk a little bit about, we've also been working on how the turbulent viscosity affect the modes, and under some conditions can excite other kinds of modes, quasi-normal modes in the disk. Okay, so that's sort of general idea, general sort of outline what we have been doing. So in the remainder of the time, just to talk about, just give you some general ideas, talk for some general concepts. How much time do I have? Okay, good. So let me, clearly I'm not going to talk about all this in great detail. I'm just going to tell you some very basic things. Explain why is that, what are these modes, and why is that this mode can grow at all. Okay, why is that out of nothing, basically, the mode can grow. Okay? Right. So let's do a simple problem. Consider waves, density waves in the disk, differential rotating disk, right? It's two-dimensional disk, very simple disk, laminar flow, the flow is moving around the black hole, right? And you consider waves in the disk, just like sound wave in this room, except sound wave in this room is simpler because the background is static, right? Here it's more complicated because my background is moving, rotating, right? So I have to, there's the complications. But essentially, it's the same problem. We are looking at sound waves in the background of differential rotating disk. Okay? So here is the density, right? Density perturbation and the velocity perturbation. When you look at waves, we have a frequency omega has azimuthal wave number m. So m specifies the azimuthal symmetry of the mode. So m equals 1 will be one-arm spiral wave. M equals 2 will be two-arm spiral wave, basically, right? M equals 0 will be axisymmetric wave, right? So, right. So this basically is density waves. Then you can look at how does this density wave propagate in the disk, right? What you find is that unlike the sound wave in this room, the sound wave can propagate everywhere. You know, everywhere in the room, the sound wave can propagate. When you have a background of differential rotation in the disk, it turns out the sound wave cannot propagate everywhere. The sound wave can only propagate in certain regions of the disk, not everywhere, only in certain regions of the disk. It's either in the region region where the radius is less than the inner limbar resonance radius, or outside the outer limbar resonance radius. What's the limbar resonance? Well, limbar resonance is the following thing. Basically, you have this wave with certain frequencies, that's sort of perturbation frequency, right? And so if you go to the rest frame of the fluid, that wave frequency will be Doppler shifted, right? So because this capital omega is differential, is rotation of the flow. So here is the frequency of the wave in the inertial frame. You see it, right? If you go to the rest frame of the fluid, the Doppler shifted wave frequency will be this. So the limbar resonance is where these Doppler shifted frequency of the wave matches the radial epicyclic frequency of the fluid, basically. Okay. Okay. So radial epicyclic frequency is related to the rotation profile of the background disk. So it depends on derivative of this r squared times omega. Omega again is the background rotation profile of the disk. Okay. So again, the key point here is that when you consider waves in the disk, differential rotating disk, the wave can only propagate in two regions. Okay, either inside the inner limbar resonance or outside the outer limbar resonance. In between there, the forbidden region, wave cannot propagate. Okay. These two regions, wave propagation, are very interesting. They're very different. Okay, outside the outer limbar resonance in this region, the wave pattern frequency, the rotation frequency of the wave as the musical direction is greater than the background. It's faster than the background rotation. So this wave has the usual property that has positive energy in the sense that when you increase amplitude, it actually is more energy. It makes sense. Just like when you have slowly moving media, a wave moving very fast, if you increase the wave amplitude, it's actually more energy. The other region is actually very peculiar. It's actually very peculiar because inside the inner limbar resonance, you have a situation where the background is rotating very fast, right? You're closer to the small radii, right? The background is rotating very fast. The wave is rotating slowly. So you have this opposite situation where it turns out you can prove mathematically this kind of wave here has negative energy. Namely, if you increase the amplitude, it actually, the total energy of the system is actually smaller, okay? This is a peculiar thing, but it is that you can actually show it's sort of because it's a little bit counterintuitive, simply because the background is rotating very fast. Okay, so now with this kind of situation, you can now look at the peculiar thing that's called a super reflection. So we can do a little thought experiment. Let me just explain what I mean here, right? So again, remember this. Again, this region is negative energy, wave in this region negative energy, wave in this region positive energy, right? So what's super reflection? So let's imagine you have a wave coming in, impinging on this wall. It will be partially reflected and partially transmitted. Okay? So let's try to do energy conservation with this problem, right? So let's say here the incoming wave have energy of -1, negative energy. -1, if this -1 is distributed between the reflected wave and the transmitted wave. The reflected wave has negative energy, -1, r squared, reflection coefficient. And then transmitted wave of positive energy is t squared. If you solve that equation, you find r squared equals 1 plus t squared. That's greater than 1. Okay? So that's called super reflection. Namely, if you have a wave coming in, the reflected wave actually has higher amplitude. So that's the intrinsic amplifier. That's how you amplify the wave. It's so because you have this differential rotation. You're using the background rotation to amplify the wave. Okay? So, so now if you imagine the inner edge of the disk is relatively sharp, you have some reflection boundary, let's say, put a wall there, let's say, right? Then you can imagine the wave can bounce back and forth here, right? Every time the wave gets reflected, the amplitude is increased. So therefore, after a while, of course, you get a trapped mode with naturally growing amplitude. The mode will naturally grow. Because every time you reflect, your amplitude is growing. So the wave trapped in this region, they can grow. So these are the modes I'm talking about. Basically, these are the modes that are basically essentially the physics of the so-called P modes. These are spiral density waves trapped in the innermost region of the disk, and they can naturally grow due to this super reflection effect. They're overstable. Okay. This problem is actually more interesting because so far I've talked about limbar resonance. In fact, there's actually something more subtle, more interesting, so-called co-rotation resonance. Okay, co-rotation resonance. So if you look at the wave with certain frequency, there's a special place in the disk where the pattern frequency of the disk of the flow of the wave, this quantity here, match the background rotation. So this is a place where the wave is rotating at the same rate as the background disk. So you can see in this special place, the co-rotation resonance, the wave and the background can talk to each other very frequently. They're just constantly talking to each other. They can exchange energy. And this is a place where you can actually, it turns out to be very important in sort of promoting the growth of the modes of the wave. Okay, so this is somewhat technical point. Let me skip this. I think on Friday or Thursday, Yuri will talk about in more detail the underlying beautiful physics of co-rotation resonance. Okay, so the key point here is that general relativity plays an important role. In order for this, the key thing is this co-rotation resonance. Let me go back a little bit. This co-rotation, what happens is that the co-rotation resonance, there can be exchange of energy between the wave and the background. The exchange of energy is two-way. Can be either from disk, from the background to the wave, or from wave to the background, and depending on the underlying property of the disk. Okay, so if you have general relativistic disk, so that the rotation profile has certain properties, then you can. It turns out you can actually use the background rotation through the co-rotation resonance to pump the energy to enhance the mode growth. Okay, so that's where general relativity comes in. With Newtonian theory, it turns out this co-rotation resonance will lead to damping. With GR, when you modify the rotation profile, the radial epicyclic profile of the disk, this co-rotation resonance can really enhance the mode. So that's where GR comes in. Not only in terms of determining the frequency, but also in terms of making the mode grow. Okay? So we've been doing this starting from a few years ago, calculating the mode property, the frequency of the mode, and also calculate the linear mode growth rate, right? And then we've been doing simulations. So here, so if you do, again, this is what I call controlled experiment, right? You set up the problem in a well-designed way. You don't put everything in, try to see under what condition the mode will grow and will saturate. So this is the nonlinear growth of the mode. You can see the spiral waves, they saturate, and they are very visible. And so here's the summary of the result. The frequency are largely consistent, not always, with the black hole mass and spin. There's some uncertainty in terms of spins, right? Especially if the spin is very large, there's some difficulty in terms of a model, in terms of getting the right frequency. But largely overall, it's we're reasonably happy. The mode frequency we calculated do not vary that much, vary by about 10% of the m dot change by a factor of 3. And you can, in principle, get the frequency ratio, basically 1, 2, 3, 4. Right? Not exactly, but close. Right? And one can understand why it's only 2 and 3 are most important, because they tend to grow faster and they're also most visible, and so on. Okay? I emphasize the mode growth is due to co-rotation resonance, where general relativity plays an important role. So this is a possible candidate for the high-frequency QPOs so far. Okay? Of course, there are complications. Black hole accretion disk is a very complicated problem. There are a lot of complications. Let me just mention a few of them we have been studying, we'll continue to study. Right? So far we've been doing thin disk, standard Shakura-Tsunaev disk, and where you basically, it's just laminar flow. In real situation, of course, there could be info, basically the disk is moving around the black hole, but near the ISCO, there could be rapid info, right, onto the black hole, right? And that info, where the gas plunges into the black hole, can lead to damping of the mode, right? So that has to be taken into account. So we have looked at this problem a bit. It turns out the mode can still survive under some conditions, not always damped. So the net result is that maybe for the thin disk, standard thin disk where you have the transonic slim disk kind of solution, the mode will be damped, but when you have when you put in some boundaries due to magnetic field, this mode can grow. So it's not surprising for us that in the standard thin disk thermal state of black hole accretion, black hole elliptic binaries, you don't see this kind of QPOs because the modes are simply damped by this info, radial info, whereas in the intermediate state or transitional state, you could have different boundary conditions where this mode can really survive. Okay. Real disk has magnetic field. We think this may be an important ingredient. So that's why another thing we have been working on is looking at the effect of magnetic field on the disk, on the modes, right? As I mentioned, magnetic field may accumulate inside the ISCO. This may actually, when you accrete a lot of mass, a lot of plasma, the magnetic flux can accumulate. There have been a number of studies on these kind of issues, and this when you have a lot of magnetic flux threading the innermost region of the disk, these can provide a good reflector in the inner region of this, and the mode can then therefore grow. And also another aspect of the B field is that when you have large-scale magnetic field threading the disk, so you have disk here, large-scale B field going through the disk. In that case, the mode frequency can be modified, and the mode growth rate can also be affected. So this is another issue. So this issue is particularly relevant for the production of jets. So here's a picture, right? You have a disk here threaded by a large-scale B field, right? And this, of course, this kind of setup is ideally suited for the production of jets, of course, right? And so it turns out with this kind of setup, the P mode property in the disk that we calculate also has some nice properties in the sense that the frequency will be closer to observed values, and also the growth rate will be larger. Okay, so that's why we think this may be more relevant for the intermediate states. Finally, let me just quickly mention something. Ongoing work, we have been working on this exciting thing. We're still digesting the result. So we have been looking at how the turbulent viscosity in the disk can affect the global oscillation, the waves in the disk. Okay, and it turns out when you have the accretion disk of black hole can have this, in addition to this global modes, the P mode I talked about, they could also have what we call quasi-normal modes in the disk. This mode would usually heavily damped if you just do ideal fluid. They're just heavily damped to quasi-normal modes. That's why it's heavily damped. The damping rate is comparable to the frequency of the mode. So that's called quasi-normal mode. But it turns out that with viscosity, turbulent viscosity, when the viscosity satisfies certain conditions, these quasi-normal mode may be excited. So here's some sort of a frequency function, frequency space diagram where you see peaks in a lot of features in variability that fluid element at different places. And this is something that we are currently working on. So here is a summary. I guess the main message, the general message is, it is for me, this is a very intriguing but also very frustrating problem, because observers, at least wrong, every time I see wrong, they provide a very well documented phenomenology there. I think, of course, it will be improved, hopefully, with Loft. But at least in the general sense, the phenomenology is well known, reasonably well established. And the theory has been sort of significantly lagging behind. And to the extent that some people say, oh, the Loft theory is hopeless to constrain any of this thing, because then you just give up, move on to some other problems, exoplanets or better problems, right? But I think it's certainly true there are a lot of ideas, but I think many of these have not been worked out simply because people are not willing to do hard calculation like Yuri did for this 5-mode coupling. This kind of really those are really important problems. So theorists need to work hard on these problems. I think that's the general message, including myself. So I talked about our own work a little bit, right? The P modes that can be trapped in the innermost region of the disk, and they are plausible candidates for these the QPOs. I wouldn't bet anything in my house for this. This is the theory. I'm just saying this is a possible candidate. We are still working on many different aspects of this. The most interesting aspect of this work is that this mode can naturally grow, right? And it's not just a clock sitting there. The clock can be amplified by differential rotation, and so they have certain appealing features. Thank you.